Hi everyone, welcome to this lecture number 2 of week 7 on the course on nonlinear systems. My name is Ramkrishna. I am a faculty member at IIT Madras, and this is a series of lectures or a course that we are offering on nonlinear systems analysis. So in lecture 1 we started defining the basic notions of bifurcation, and essentially this analysis had to do with what happens to the stability or some qualitative properties of a system as a certain parameter is varying. So far we were interested in existence and uniqueness of solutions, we were interested in stability. We had different notions of stability via the linearization, the Jacobi linearization, and then we characterize equilibrium points as stable and unstable nodes, focus, center, and so on. Right. So last time we or in the previous lecture we had few notions of bifurcation, starting with so the linear system was pretty clear, right? You either move, so the only change that could happen or a qualitative change that could see drastically is when your poles move from the stable region to the unstable region, whereas in the nonlinear case you can have a bunch of things happening, right? For example, in the saddle node bifurcation you have an equilibrium point which was a stable focus, a saddle as the parameter varies at mu equal to 0 and for mu less than 0 this equilibrium point just disappears. So you had two equilibriums, one of which was stable, one of which was unstable. As the parameter value of the parameter mu changed to a negative value, these equilibriums disappear. Next we had things where you had two equilibrium points, one saddle and one stable focus, and as mu goes from less than 0 to mu greater than 0, they just interchange their properties. So the stable node becomes a saddle and vice versa, the saddle point becomes a stable node. Third, we checked how in the supercritical Pitchfork bifurcation that for mu less than 0 we had a stable equilibrium point, and as mu changed its value to greater than 0 we had this stable node becomes a saddle, and then you have two other equilibriums which emerge out of almost nowhere. And this is a good bifurcation or a safe bifurcation to happen, because your system trajectories, even though after the bifurcation point they will just settle down to some points close to the equilibrium point for small values of mu. And then you had the reverse happening where you had a stable node here, and then for mu less than 0 you had two saddle points here. As mu faces a transition from from a negative value to a positive value, this actually becomes an unstable point, and this is typically called an unsafe bifurcation. Last, we also showed an example where for mu less than 0 we had a stable focus, and then for mu greater than 0 the stable focus became unstable, but all the trajectories converge to some limit cycle here, right? And this was something nice that we actually saw. So this is called Hopf bifurcation, and this is safe, and okay, there are other examples of unsafe Hopf bifurcations, but we will skip those examples for now. But so what is the common point here if we start from the saddle node bifurcation is when mu equal to 0 you experience a 0 eigenvalue. Similarly, as mu changes signs, the system or the linearized version is essentially associated with a 0 eigenvalue. That is true even in the transcritical bifurcation, it is true also for the Pitchfork bifurcation. So the only thing that changes when you look at Hopf bifurcation is that your eigenvalues are such that they pass through the imaginary, like a pair of eigenvalues which were originally here, they will pass through the imaginary axis this way. So you will have roots on the imaginary axis, and possibly they could go to the unstable region. And then we also had things to derive on how what decides the radius of this limit cycle or the properties of the limit cycle based on this parameter value mu. Okay, so in much of this, if you look at examples, uh, everything was depending only on x1, right. So the parameter mu had nothing to do with x2. In this equation, it was true for saddle node bifurcation and so on, except when you were looking at the Hauff bifurcation case. So all these essentially characterize 1D bifurcations, right. So I can just study little more extensively just based on these, the first equations on x1 dot here, this equation here, this equation here and so on, except here where I am just looking at a system where the mu changes, or mu or x1 and x2 both depend on this parameter mu. So this is a 2D bifurcation. So what we will do now is to look at properties purely from the first equation that we had, right. So the first property that we see, which is generic across all the bifurcations, is that of a 0 eigenvalue. Okay. So essentially this means that if I have my system f depending on x and mu, this essentially means that df, or the partial of x, f by partial of x at some parameter value x, at some state value mu 0, sorry x 0 and mu 0, this will go to 0, right. Or in our case, this just turns out to be that the origin. So and then for mu being actually being equal to 0. Okay. So this we will see of how we can relate to each of these properties now, or can we derive some patterns and in general conclude given a system what kind of bifurcation is likely to occur, if at all. Okay. So we start with the first example of the saddle node bifurcation. Okay. In this case, what we have is f x comma mu, which was x dot, was of the form x minus mu square, and we are talking of 1D bifurcation. So x and y both will belong to the real line. Okay. So first, it is easy to check that f at 0 0 is equal to 0. Next, it is also easy to check that the partial of f with the partial of x at 0 0 is also equal to 0. Okay. Now next is first, what happens, what are the fixed points? You can also call this as what are the equilibrium points. Okay. And it is easy to check that okay, this occur when x minus mu square equal to 0, or the fixed points of this system are x is plus minus square root of mu. Okay. So first thing is one, that there are no fixed points when mu is less than 0, and second, when mu is greater than 0, there are two fixed points. This one, right, plus or minus mu, plus or minus square root of mu. Okay. If I were to just draw a graph which tells me some relation between x so around, so when I am at equilibrium, or so my equilibrium points are given by this one, right. So x, if I just call this x star, is square root plus minus mu, I am just having x equal to mu square, something like this, right. So all points on this curve are the equilibrium points. Okay. So some of them are stable So, so this is so okay. Let's check how. If I were just to plot what the relation between mu and x, okay. So here I can easily find out, right. So which of the equilibrium points is stable and which one is unstable. So the plus square root of mu is stable, as we saw also in the previous lecture, and the negative of square root of mu is an unstable equilibrium point, right. Okay. So how does this picture now look like? So if I were to say, okay, let's give me a green color for the stable regions, this would be the stable region, this is the unstable region, and everything is characterized by mu is x square. So what we see from this picture here is that when mu is less than 0, there are no equilibriums. For mu greater than 0, the equilibrium points mu move through this green line, which is stable. So if I were to draw the vector fields around this, so the vector fields typically would be something like this. So they would approach this point and so on, okay. Whereas the red line or the red curve is typically, it represents this part of the equilibrium. So for all values where x is the square root of mu with a negative sign, you are looking at an unstable behavior, which means if I plot the vector fields, so all points in this are the equilibrium points. So if I plot the vector field around this, they will just, the trajectories will just move away. If this is my equilibrium point, the trajectories will just move into the equilibrium point, right. And for all values here, the eigenvalues or the system will just go to infinity. So there are no equilibrium points in this region. So you have three regions, right. You have no equilibriums, you have a stable region represented by the green line and an unstable region represented by the red line. So at any point here, my vector fields would simply be just this way, and here they would just move away from the equilibrium points. So each point on this red line is an unstable equilibrium point, each point on this green line is a stable equilibrium point. So these are typical bifurcation diagrams, as they call it. So a bifurcation plot where you just check how the equilibrium points or the vector field changes with varying values of mu. Okay, so the next bifurcation. So this was the simpler, the first case of the saddle node bifurcation. Right. So we had one stable equilibrium point, and another unstable equilibrium point. So the next one we will have is x dot is f x comma mu, which now takes the form mu of x minus x square. Okay. Again, mu and x both belong to the real line. So 1, okay, this is easy to check. This is also easy to check. 0, 0 is 0. Okay, so first is how many fixed points? How many equilibrium points or fixed points? I will use these words interchangeably, but they actually mean the same. So I have x equal to 0 is one fixed point or equilibrium point, x equal to mu is another fixed point. Let us check the situation when mu is less than 0. In this case, x equal to 0 is stable and x equal to mu is unstable. You can check this by the Jacobi linearization or even what we did in lecture number 1. Second case is you have mu greater than 0, in which case x equal to 0 is now unstable and x equal to mu is now stable. Okay, let me just draw the bifurcation plot of this. So, again I am drawing curves between mu and x, and I just want to check what happens as mu varies. Okay, so first x equal to 0, let's focus on this one. X equal to 0 is stable when mu is less than 0, which essentially means so this is the x equal to 0 line, right here. So this is stable when mu is less than 0. Okay, now mu greater than 0, the same equilibrium x equal to 0 becomes unstable. So I just plot it this way. Okay, and then you have the line x equal to mu, right. So how does this look like? X equal to mu when mu is less than 0 is unstable. So I am just in this region. This is the line x equal to mu. Okay, and the same line when x equal to mu for positive values of mu is a stable line. This is again x equal to mu. So all the green lines are stable and the red lines are stable. So this will just show you, right, how so what happens in this case is just that you have the two equilibrium points what they do is they just exchange stability. The stable one becomes unstable and the unstable one becomes stable. Okay, good. We go to the next one. I have x dot is f x comma mu x minus x cube with again x and mu both being in the real line. Okay, so this is easy to check. F 0 comma 0 is 0 and the partial of f with partial of x 0 comma 0 is also equal to 0. Okay, what are the equilibrium points? Equilibrium points for this system are as follows. So for mu less than 0, there is one fixed point x equal to 0 which is stable. So you can also compare with what the pictures we had earlier, right. So this one. So I'm now over here. In the previous case, you can just check what is happening here, right. That the red dot becomes green and the green one becomes red for the transcritical bifurcation. So what I'm drawing here is a different version of what I drew in the first lecture. Okay, so now we are in this Pitchfork bifurcation case. Okay, so mu less than 0, there is one fixed point x equal to 0 which is stable. Same was the case here also, right, this one. So this is the case of Pitchfork bifurcation. Okay, and for mu greater than 0, you have x equal to 0 which is now unstable, and in addition you have two new fixed points which are given by x square equal to mu or x equal to plus minus square root of mu, and both of which are stable. Okay, so if I were to draw the bifurcation diagrams, this is again mu versus x. Okay, so for mu less than 0, the point x equal to 0, which is this line, is stable, this one. Okay, this is stable, and the vector field will be just pointing towards this line. Okay, if I were to plot the vector fields here, they would just be, so that will approach these points, approach these points, go away from these points, approach these points, approach these points, go away from these points. So whenever you have this unstable equilibrium, the arrows naturally will point outwards, and when there is a green line, the arrows naturally will point inwards, and you can just keep on drawing this. Okay, so similarly here, right? So when x equal to 0, what I have is an for mu less than 0, x equal to 0 is stable. For mu greater than 0, this becomes unstable in such a way that the vector field will just point outwards. Okay, and then what else is the other equilibrium condition? You have x square equal to mu. X square equal to mu, we know, looks something like this, right? And x square equal to mu, which was a parabola like this. Okay, so this is stable in both cases, right? So I'll just have a green line here. Sorry. Okay, not the best of drawings, but okay, good enough for explanations here. So this will converge here, this and this. Well, a little contrast to what happened in the first case. So for in this region, x greater than 0, we had a stable equilibrium points, x less than 0, we had unstable equilibrium points. Whereas here, well, on both regions I have stable equilibrium points. Okay, so this is how we can look at pitchfork bifurcation. So the other case will be very similar. X dot is f fxu. So this was the supercritical thing, right? In the subcritical thing, we had mu of x plus x cube. Okay, in which case for mu less than 0, we had 3 equilibrium points. One was x equal to 0, then we had this was stable, and then you had x is plus minus square root of mu, which were both saddle or unstable. For mu greater than 0, we had only one equilibrium point, that was x equal to 0, and this was saddle, or inverse, or in other words, unstable. So if I again draw the bifurcation diagram, it will look pretty neat. So mu x, then I am looking at this region. So this region typically is the mu less than 0 region. This is the mu greater than 0, mu less than 0. So x equal to 0 was stable. So this remains the way it is, and for x mu greater than 0, there is only one equilibrium point, which looks like this. Okay, and for mu less than 0, I am looking at this curve x square is mu, and there will just be a series of unstable points like this. Sorry. Right, so these are, so if I just were to plot the vector fields, they'll just go in here, go away from the red line, and here they just keep going away. Okay, so here I just changed from a stable to an unstable equilibrium point from mu less than 0 to mu greater than 0. Okay, so okay, we will not do the Hopf bifurcation, that's the 2-dimensional case. We will stick to 1-dimensional case, and what we will try to find is given a set of equations x dot equal to f of x and u, can I derive certain necessary and sufficient conditions which will ensure or rule out the presence of certain bifurcation points. So, the last example that I would like to do here is this one. X dot is f x comma mu, which looks like this. This is mu minus x3. Okay. So the reason I am doing this example is okay, will be obvious. So let us say I am looking at the situations again, f 0 comma 0 is 0, the partial of f by partial of x at 0 comma 0 is also equal to 0. Okay. What are the fixed points or the equilibrium points? The equilibrium points are given by mu is x cube. Okay. Now, now for mu less than 0, this is the system has a unique stable equilibrium point. Similarly, as mu is greater than 0, this will all be the same, this will be a unique and a stable equilibrium point. So, what happens is that the dynamics are qualitatively the same. Both for mu less than 0 and mu greater than 0, which means there is no addition or deletion of equilibrium points. If an equilibrium point was stable for mu less than 0, it continues to be stable for mu greater than 0. So, in this case there is actually no bifurcation. Okay. So the reason I am doing this is one may think that whenever this happens, right, that you may think that there is actually a possibility of a bifurcation. It was true here, it was true here in the case of transcritical bifurcation, it is also true in the case of the saddle node bifurcation. So, whenever I satisfy these conditions, it does not guarantee existence or not of bifurcations. Okay. Right. Okay. So, then we will look at, okay, what are the conditions then? How does one derive conditions? For existence of certain bifurcation. Okay. So, so before we do that, I will just tell you some result that we will use from calculus, and that has to do with the notion of what we call as the implicit function theorem. Okay. So, there are more general notions of this, but we will stick to functions f x y comma 0, where x and y both belong to R. In general, x can belong to R n, y can belong to R m, and so on, and f can lie in R m. So, here I am just talking of a very simple function. Okay. So, the question that we will ask, and it will be obvious why am I doing this before I derive necessary sufficient conditions for existence of bifurcation, is I just start by asking a question: can I uniquely solve for y in terms of x, right? So, given this, or in other words, can I write y as some function of x in this? If I can write, can I write it in all conditions? If I cannot write it in all conditions, what are those conditions? So, we will just derive that with the help of some small example. Okay, so let's start with this simple example. It's like example which most textbooks teaching implicit function theorem would do. So I have x square plus y square minus 1 equal to 0, and the reason I do this is it's nicer to interpret. So the question is, can we express a portion of the unit circle, and it will be clear why I am saying the portion of the unit circle as a graph of a function, this one. Say not y of x, but say y equal to some g of x. Okay, so what I know is that with these equations I can easily write these things, right, that y, I can solve for y given x via this expression whenever y is greater than 0, and for when y is less than 0 I can use this expression. Okay. Additionally, there is no well defined solution near these points, plus minus I think it should be plus minus 1 comma 0. So when x equal to plus 1 or x equal to minus 1, there is no unique solution, because if when I say x equal to plus 1, I will get a 1 here, when x equal to minus 1, I will get a minus 1 here. So there is no unique sign of the square root. Okay, now a close observation, and which we will try to also justify in more general setting, is that at this, and these are the points, right, where no unique sign of the square root happens, is precisely the points when df or the partial of f with partial of y equal to 0. Okay, this is at plus or minus 1 comma 0. Okay. So this is a little motivation for the implicit function theorem. What it also means is, if I were to just draw a little schematic to explain from the circle itself. So I just take in this, I just take a little circle. So, okay, assume this looks like a circle. Okay, and just say I take a point A here, right, and a little area or a little neighborhood around that point A, and I call, sorry, this A here and a little neighborhood around that point which I call, oh, sorry, A say, sorry, this is A around a point A, this is point A, then I can do this. Can find a point B, and for all of this region I can find a little region here called capital B. Then similarly I can do it on the other side of the circle also. So here I can find a point, say B prime, and some area around the area B prime. This one I call this as B prime, and this dotted, this area, darkened area here as B, so not B prime, this is B. So if I were to write it more formally, I can say if we choose A comma B with f A comma B equal to 0, again I rule out these points that A should not be equal to plus or minus 1 for the reasons explained earlier. So there are open intervals A which contain A and open intervals B which contain this small b, such that or with the property that if x is in A, there is a unique y in B such that f of x comma y is 0. Okay, like if I look at just the upper portion of the circle where this y is greater than 0, then give me an A, I can find a unique B which will relate A and B. Okay, and therefore we can define a function g again from A to R says that g of x, so this is all the B is the g of x, g of x belongs to B, and now the function where I started off saying that f x comma y is 0 can now be written as f x comma g x is equal to 0. And this is when I am just, let's say I am looking at the region B is greater than 0. Okay. So, when B is greater than 0 in this region, then I can say that this g of x can be uniquely identified by 1 minus x square. Okay. Similarly, if I am looking at say B1 where this is less than 0 such that f a comma B1 is less than 0, so over here, or B prime. Then I have another function f x comma g x equal to 0 where g1, okay, I call this g1, g1 of x belongs to B1, and this g1 of x is uniquely represented by square root of 1 minus x square. Okay. And not only that, this both g and g1 are differentiable. Okay. So, again the idea is, given a function of this form, when can I write y as a function of x? Okay, and under what conditions I can write. Okay, so let us go back to these conditions here. Okay, so let us say, okay, so I am just looking at f x comma y equal to 0. Okay, I can just do some basic calculus and say that, okay, df by dx plus df by dy, or the partial of df by dy by dx equal to 0. I can frequently write this as this. So, I am just writing a very simpler crude version of what I am trying to say. So, I want to write y as a function of x, or can I solve for y as a function of x? Which essentially means that I am looking at a solution to these equations. Dy by dx is minus partial of f, partial of x, partial of f by partial of y. Okay, so I can just, by looking at these expressions, just say that, well, I can solve for this assuming that the denominator does not go to 0. It essentially means that df by dy, or the partial of f with partial y, should not be equal to 0. Right. And now we are ready to state the general theorem now, right. So, suppose f is from x to r for some a, something wrong here, this f should be x comma x to r, okay, and for some f a b, and for some points a and b we have f a comma b equal to 0. There are a bunch of points you can find on the circle. So, if df by dy at that point is not equal to 0, then the equation f x comma y has a unique solution y equal to g comma g of x, where y is defined in some neighborhood B of R, right, and then this A is, so this A belongs to A as I explained previously. Then I can write that f x g x equal to 0 for all x belonging to A, and not only that, we find that the function g is differentiable. Okay, I will not really do the proof of this, that is not really important, but we will try to understand how to apply this particular proof to get to our results. That will come up in the next lecture. Thanks for watching.